Calculating principal values. Hello everyone. Let's begin our session on calculating principal values. To start, let's look back at what we have already covered. In our previous subsections, we established that trigonometric functions are periodic. In simpler terms, this means that these functions repeat their values over and over again at regular intervals as we move along the axis. Now, because they repeat, they do not naturally have a one-to-one relationship, which makes creating an inverse function tricky. To solve this, we restricted their domains to specific, limited intervals. These chosen intervals are known as the principal value branches. This is a crucial distinction because when you are evaluating an inverse trigonometric function, you will find that there are actually infinitely many angles that could produce a specific value. However, in mathematics, we need a single, consistent answer. Therefore, the principal value is defined as the one unique angle that falls within the predefined principal value branch. Understanding how to identify and calculate this specific value is critical for your grade 12 mathematics curriculum. Over the next few slides, I will guide you through a pedagogical, step-by-step approach to ensure you can find these values accurately every time. Step-by-step pedagogical approach. Now that we have established what principal value branches are and why they are necessary, let's move on to the actual process of calculating these values. To find the principal value of an inverse trigonometric expression, I want you to follow these systematic steps. First, we begin with step 1, assignment. In this step, we simply set the given inverse trigonometric expression equal to a variable, which is typically represented by y. For example, if you are working with an inverse sine function, you would start by writing, let y equal the inverse sine of x. Once we have assigned a variable, we proceed to step 2, conversion. Here, we rewrite the equation by moving the inverse function to the opposite side. The purpose of this is to convert the inverse trigonometric equation into a standard trigonometric equation, which is much more familiar and easier to manipulate. For instance, if our previous step was y equals the inverse sine of x, then after conversion, it becomes sine of y equals x. These first two steps set the foundation. In the next slide, we will look at how to identify the correct angles and select the one that fits within the required branch. Step-by-step pedagogical approach, continued. Now that we have assigned our expression to a variable and converted it into a standard trigonometric equation, let us move on to the final 3 steps of the process. Starting with step 3, we focus on the identification of potential angles. At this stage, you will look at your unit circle or refer to your standard trigonometric tables to find the angles that satisfy your equation. For instance, where the sine of y equals x because trigonometric functions are periodic, you will likely find more than one angle that works. This leads us to step 4, which is the most critical part of the process. Selection based on the principal value branch. As we mentioned at the beginning of this lesson, we must restrict our search to a specific interval to ensure we get a unique answer. From the potential angles you identified in the previous step, you must select the one that falls within the range of the principal value branch for that specific function. To be precise, for the inverse sine function, the angle must lie within the closed interval from negative pi over 2 to pi over 2. For the inverse cosine function, the angle must be within the closed interval from 0 to pi. And for the inverse tangent function, the angle must fall within the open interval from negative pi over 2 to pi over 2. Once you have identified the correct angle within these boundaries, you proceed to step 5, the final statement. Here, you simply state the final principal value as the value of y. To help you better visualize why we restrict these values to a specific branch, I will now share a conceptual analogy, and then we will walk through some detailed examples to put these 5 steps into practice. Conceptual analogy, the standard address. Now that we have covered the technical steps for calculating the principal value, let us use a conceptual analogy to understand why this process is necessary. Imagine you are giving someone directions to a specific house. you could simply tell them to walk straight for 1 kilometer. Alternatively, you could tell them to walk straight for 1 kilometer, then spin around in a full circle of 360 degrees, and then stop. Now, logically, both sets of instructions lead the person to the exact same house. However, the first option is clearly the most direct and standard way to reach the destination. Similarly, in trigonometry, the principal value serves as the standard address of the angle. Because trigonometric functions are periodic, there are infinitely many angles that can produce the same value. By focusing on the principal value, we avoid unnecessary rotations around the unit circle and ensure we arrive at a single, unique answer. With this conceptual foundation in place, let us now move forward to some detailed examples to see how these steps and this logic are applied in practice. Detailed examples. Now that we have discussed the theoretical framework and the 5-step pedagogical approach, let us apply these steps to a concrete problem. Please look at example 1, where we are tasked with finding the principal value of the inverse sine of 1/2. Starting with step 1, we begin by assigning the expression to a variable. Let us set y equal to the inverse sine of 1/2. Moving to step 2, we perform the conversion. We rewrite this as a standard trigonometric equation by moving the inverse function to the other side, which gives us sine of y equals 1/2. In step 3, we identify the potential angles that satisfy this equation. Based on the unit circle or standard trigonometric tables, we can see that both the sine of pi over 6 and the sine of 5 pi over 6 equal 1/2. Now we reach the most critical part in step 4, selecting the correct angle based on the principal value branch. As we established in the previous slides, the principal value branch for the inverse sine function is restricted to the interval between negative pi over 2 and pi over 2. When we compare our two angles, we find that pi over 6 falls within this interval, whereas 5 pi over 6 does not. Finally, in step 5, we make our final statement. Since only pi over 6 satisfies the range requirement, the principal value is y equals pi over 6. This process ensures we find the unique, standard address of the angle, avoiding the ambiguity of the periodic nature of trigonometric functions. We will now apply this same logic to cosine and tangent in the following examples. Detailed examples continued. Now, let us move on to example 2, where we will find the principal value of the inverse cosine of negative 1/2. We will apply the same 5-step pedagogical approach we discussed in the previous slides. Starting with step 1, we begin by assigning the expression to a variable. Let us set y equal to the inverse cosine of negative 1/2. In step 2, we perform the conversion. We rewrite this as a standard trigonometric equation by moving the inverse function to the other side, which gives us the cosine of y equals negative 1/2. For step 3, we need to identify potential angles from the unit circle that satisfy this equation. We can see that both 2 pi over 3 and 4 pi over 3 have a cosine value of negative 1/2. Now we reach step 4, which is the most critical part of the process, selecting the angle based on the principal value branch. As we noted in our earlier slides, the principal value branch for the inverse cosine function is restricted to the interval between 0 and pi. When we compare our two potential angles, we find that 2 pi over 3 falls within this interval, whereas 4 pi over 3 does not. Finally, in step 5, we make our final statement. Since 2 pi over 3 is the only angle that satisfies both the equation and the range restriction, the principal value is y equals 2 pi over 3. Detailed examples continued. Now that we have explored the principal values for sine and cosine, let us apply the same pedagogical approach to the tangent function in example 3. We are tasked with finding the principal value of the inverse tangent of negative 1. Following our established process, we begin with step 1, assignment. We set the given expression equal to a variable, so we let y equal the inverse tangent of negative 1. Moving to step 2, we perform the conversion. We rewrite this as a standard trigonometric equation by moving the inverse function to the other side, which gives us tangent of y equals -1. In step 3, we identify potential angles. By referring to the unit circle or our trigonometric tables, we can see that there are multiple angles that satisfy this equation. Specifically, the tangent of -π/4 equals -1, and the tangent of 3π/4 also equals -1. Now we reach the most critical part, step 4, selection based on the principal value branch. As we discussed in the earlier slides, the principal value branch for the inverse tangent function is the open interval from -π/2 to π/2. When we compare our potential angles, we find that -π/4 falls within this interval, whereas 3π/4 does not. Finally, in step 5, we provide our final statement. Since -π/4 is the only angle that resides within the predefined branch, the principal value is y equals -π/4. Pay close attention to how we handled the negative sign here, as this leads us directly into the common mistakes we will discuss in the next slide. Common mistakes to avoid. Now that we have walked through the step-by-step process and seen several examples, let us discuss some common pitfalls to ensure you avoid these mistakes in your exams. First, let's address the issue of ignoring the range. A very common error is providing any angle that satisfies the trigonometric equation without checking the restriction. For example, if you are calculating the inverse sine of 1/2, you might be tempted to say the answer is 5π/6. While it is mathematically true that the sine of 5π/6 is 1/2, this angle does not fall within the required interval. You must always verify that your final answer lies strictly within the principal value branch we established in the previous slides. Second, be mindful of incorrect sign handling. This is a helpful rule of thumb for checking your work. For inverse sine and inverse tangent, if the input value is negative, your principal value must also be negative, falling within the interval from -π/2 to π/2. However, inverse cosine behaves differently. If the input for inverse cosine is negative, the principal value will not be negative. Instead, it must be an obtuse angle, falling within the interval from π/2 to π. Finally, let's clear up some notation confusion. It is very easy to confuse the notation for inverse sine of x with 1/sine of x. Please remember that inverse sine of x is an inverse function used to find an angle, whereas 1/sine of x is the reciprocal of the sine ratio, which is known as the cosecant function. These two are entirely different operations. Keep these 3 warnings in mind as we move forward to our final key takeaways. Key takeaways. All right, let's wrap up everything we have discussed in this lesson with these key takeaways. First, remember that the principal value is the one unique angle for an inverse trigonometric function that falls specifically within its defined principal value branch. As we discussed earlier with our standard address analogy, this ensures we have a single, consistent answer rather than infinitely many possibilities. Secondly, recall the step-by-step process we applied in our examples. To find this value, we convert the inverse function back into a standard trigonometric function. In other words, if y equals the inverse function of x, then the function of y equals x. This conversion is the foundation for solving these problems. Finally, the most critical part for your grade 12 mathematics exams is memorizing these specific ranges. For the inverse sine of x, the principal value must lie between -π/2 and π/2, inclusive. For the inverse cosine of x, the range is from 0 to π, inclusive. And for the inverse tangent of x, the value must be between -π/2 and π/2, though note that for tangent, the endpoints are excluded. By keeping these ranges in mind and following the conversion process, you can avoid the common pitfalls we discussed and accurately calculate the principal value every time.